OBS එකේ දෙකක් ක්ලික් කරලා OBS එකේ වර්ණය මේක දෙක තුනක් ක්ලික් කරන්න ඊට පස්සේ ඒ මොකද මාර වෙනවා මේ වැඩ නෙමෙයි ඒක බලන්න
Check. Online students, can you hear me clearly? Online students, can you hear me clearly? Can someone please confirm? Online students, can you hear me clearly? Okay, thank you. Okay. So today we have to like start and continue fields, specifically gravitational fields, right? And for like the previous lesson for optics, I have uploaded all the required like answer scripts. So you can find in the group, you can find the optics exercise all the exercise answer scripts too. And past paper tute is available, and the students who didn't come last week, they can get the past paper tute. Just try the whole past paper tute, and I'll provide the recordings of the remaining questions. Okay, I'll provide the discussion recordings of the remaining questions of the past paper tute. Then let's move to the new lesson, gravitational fields. And today from around 6:30 to 8:30, you have the heat lesson as usual. Okay, so the normal schedule is from 6:30 to, sorry, from 3 to 6, around 6:15, you have gravitational now, and from 6:30 to 8:30, you have the heat lesson. Okay, we are doing two lessons parallelly with the target of finishing the syllabus on time. So that is the plan. Like talking about fields, everyone got the tutes? Anyone need tutes? Anyone? Okay, well, tutes in the and tutes will be available in the Zoom chat too. And we have delivered a lot of tutes by now, so I hope a lot of students may have received the tutes. But if you haven't received the tutes yet, I mean, we have like sent the tutes up to static electricity. So all the tutes until like maybe not September, until the end of October, you will receive. Okay, all the tutes required for not actually October. Yeah, for all the tutes until you need until October, November, you will receive this time. Okay, so that we can make sure that there are no delays after this point in tute delivery. Uh, so you may receive the tutes. Otherwise, if you haven't received them, like you will receive, if you previously requested for them, you will definitely receive it within like 1 week. If not, please send a message. I'll provide you a number when the session is going on. Contact that number, put a message to that number requesting for the tutes again. And the new students definitely put a message to that number requesting for the tutes. We'll send you the required tutes, and I mean all the required tutes that are required until maybe mid-November. Okay. So talking about fields, what is a field? First of all, before moving into gravitational fields or anything, we have three types of fields in our syllabus. Okay, we have to learn gravitational fields. We have to learn static electric fields. Then we have to learn magnetic fields. These are the types of fields that we have to learn in the syllabus. So before continuing with any type of field, first we should know what is a field. What is a field? So talking about what is a field, it actually has a mathematical definition. Okay, field is a mathematical term. Well, they are requesting for the English medium tute. Just check. So it is actually a mathematical term. Field is a mathematical term. That means if you have an area or a volume or any fabric anywhere that you can assign values to each point. That means take this atmosphere. It is a system. If you have a system and if you can assign values, okay, if you can assign values to that system, each point of that system, okay, we call that is a field. That means take this atmosphere, consider the temperature. In this system, temperature is a field, okay? In this system, temperature is a field. Why? You can assign temperature values, okay? You can assign temperature values for each point, right? Clear? You can assign temperature values for each point. The temperature here is maybe 30. Temperature here maybe 30.5. Temperature here maybe 29. Everywhere in this whole, I can assign a value to each point, right? Mathematically, that is a field, okay? For more examples, pressure. You can define a pressure everywhere, right? So it is a field. That means it's a pressure field. What is the meaning of a pressure field? That means you can define a value for a physical quantity everywhere in a system. Clear? That kind of a simple, I mean, the definition of a field is simple like that. Clear? It has a very simple definition like that. Then moving forward, like, what about the like force fields? So in this syllabus, we specifically discuss about force field. What are force fields? What are force fields? Force fields are still a field, but with a force. With a force. That means if you can define a force for each point of a system, then it is a force field. That means, for an example, yes, I know that we have to learn about gravity, but even without knowing that part, we know the definition of gravity, right? We know the definition of a gravitational field. Okay? And if there are any Sinhala medium students, Sinhala medium ළමයි ඉන්නවා නම් ඔයගොල්ලෝ join වෙන්න ඕනේ mainly Sunday class එකට if possible, okay? Sinhala medium ළමයි ඉන්නවා නම් ඔයගලන්ට සිංහල teach කරන class එකක් ඕන නම් join to Sunday class if possible. Then, like, for an example, take gravity. Gravitational field. What is the meaning of gravitational field? In a system, if you keep a certain mass, that mass will always feel a force. That mass will always feel a force due to gravity, right? So I can tell the gravitational pull here is this value. 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 So I can define a force to each point in a system, right? Clear? So these kind of fields, we call them force fields. Clear? We call them force fields. That means you can define a force for each point in a system. Clear? Clear? That's how we define a force field. Then, again, like, there are more examples. In our syllabus, we mainly learn static electric fields and magnetic fields too. There are also, these are force fields. Why? Take static electric fields. Positive charges attract negative charges and negative charges attract positive charges. So what actually happens is, in a static electric field, a static electric field will create a force on a charge. So just like how the gravitation acts on mass, a static electric field acts on charge. Clear? So if you can keep a charge here, what is the force acting on that? If you can keep a charge here, what is the force acting on that? If you can keep a charge here, what is the force acting on that? Clear? If you place a charge at a certain point, what is the force acting on that? That is another type of a force field. We call that static electric field. Clear? Then again, magnetic field. We have some kind of a magnetic field here, right? We have a magnet in Earth's magnetic field, and there are huge current wires going everywhere. Huge current wires creates magnetic fields. Clear? So due to that, if you keep a magnetic north here, what is the force acting on that magnetic north? If you keep a magnetic north here, what is the force acting on that magnetic north? Like that, Magnetic force field means there's a system and you can define the force acting on each point of that system. Clear? Clear? So this is the simple definition of a force field. Clear? Then we move to our lesson, okay, which is gravitational fields. Okay, we had to learn gravitational fields. So as you know, what is gravitational field? A gravitational field means in a system, there's always, okay, gravitational field is a field that exerts a force on mass, right? Clear? Gravitational field is a field that can create a force on a mass. Clear? So, so when we are learning about gravitational fields, first we should learn some terms, okay? First we should learn some terms related to gravitational fields, okay? We should learn some terms connected with gravitational fields. So the first term is gravitational field intensity. First term is gravitational field intensity. What is gravitational field intensity? It's just a term that we have to learn about gravity. Gravitational field intensity is the gravitational force acting on a unit mass. Clear? Gravitational field intensity is the gravitational force acting on a unit mass. That means if you keep a mass, if you place a mass, this is a system. This is a system and you have a gravitational field everywhere. And you place a mass here. You place a mass m here, and the gravitational field creates a force F on that mass. Clear? Gravitational field creates a force F on that mass. Clear? Then our gravitational field intensity E, gravitational field intensity is force over mass, right? Gravitational field intensity is force over mass. Clear? F over m. F over m means the force acting on a unit mass. Clear? The force acting on a unit mass. Clear? That means if you place a 1 kilogram mass, what will be the phase? What would be the force acting on that? Okay. So that's gravitational field intensity. The dimensions you can find, dimensions and unit you can find, right? So here it's Newton, here it's kilogram. So the units are Newton per kilogram. You can solve this and find the dimensions too, and the dimensions are available in the tute. Next, the next term is gravitational acceleration. Next term is gravitational acceleration. So what is gravitational acceleration? Gravitational acceleration is something that we know. Gravitational acceleration is the acceleration felt by an object due to gravity. In usually, what is the value of gravitational acceleration? The value we know, 10, right? 10, or more accurately, 9.81. In this syllabus, in this lesson, gravitational acceleration is not always 10, okay? Why? Gravitational acceleration definitely changes from point to point, right? Here it's a different gravitational acceleration. On top of Everest, it's a different gravitational acceleration. And in the moon, gravitational acceleration is different. Why? Gravitational pull is different. So gravitational acceleration is not actually 10. It is a variable, okay? It is a variable. Why do we always consider gravitational acceleration as 10 in our syllabus when we are doing mechanics question? All the mechanics questions happen in ground level, right? Okay. Almost all the mechanics questions happen in ground level, right? Okay. They never tell you have a system on moon, then we usually don't see questions like that, right? Okay. Usually all the mechanics questions happen in ground level. So in ground level, gravitational acceleration is approximately 10. Clear? But it should change from place to place, it changes, okay? So when I'm teaching, in the tute, we refer to gravitational acceleration as G, okay? We refer to gravitational acceleration as G. But when I'm teaching, I would use two symbols. I would use G for 10. Still, I would use G for 10, okay? Okay? I would use G dash for gravitational acceleration when I'm teaching, okay? Because gravitational acceleration is a general term. It is that the gravity can change everywhere, right? Clear? So gravitational acceleration is something that could change. So in the tute, we use G for gravitational acceleration and it can change. But when I'm teaching, I would use these two terms. Otherwise, it would be confusing. I would use G dash for gravitational acceleration, general term. I would use G to represent 10. Okay. I would use G to represent 10 when I'm teaching. In the tute, we can't do that because the official symbol for gravitational acceleration is still G. When I'm teaching, I would do this. Okay. Okay, so one more thing, gravitational acceleration is equal to gravitational field intensity, okay? Gravitational acceleration is equal to gravitational field intensity. Why? I mean, uh, how do I get gravitational acceleration of something? How do I get gravitational acceleration of something? I apply F equals ma, right? I apply F equals ma. So the force acting is F, mass is m, acceleration is g dash. Acceleration is g dash. Clear? Force F, mass m, acceleration is g dash. Clear? Then the acceleration is going to be g dash equals f of m. So it's the same, right? F of m, f of m. Clear? So gravitational field intensity equals gravitational acceleration. Clear? E equals g dash. Clear? Gravitational field intensity equals gravitational acceleration. Clear? Clear? Okay. So these are the things that we should know regarding the terms until this point, okay? Then let's learn the first theorem related to gravity. First theorem related to gravity is Newton's law of gravitation. Newton's law of gravitation. First theorem is Newton's law of gravitation. That is how this gravity happens. What is the source behind gravity? What creates gravity? When it comes to that, Newton defined an experimental law related to gravity, okay? Newton defined an experimental law related to gravity, which is Newton's law of gravitation. So in that experimental law, what he mentioned was if one mass is m1, if one mass is m1, another one is m2, between two masses, definitely a force will act. Clear? Okay. A force acts on a mass. Okay. So what they mentioned was when a force acts like this, okay, these two forces are equal. Why? These two are an action reaction pair. Clear? That means this force occurs on this one due to this guy, and this force occurs on this one due to this guy. Clear? So it is a mutual force acting between them. Clear? Okay. When there is a mass in a system, okay, between each particle, a mutual force would act between them. Clear? A mutual force would act between them. Clear? That he called the gravitational force. Clear? That he called the gravitational force. And if the distance between the center of gravity of these particles is r, if the distance between the center of gravity of these particles is r, then the law was this force F equals, F is proportional to m1. That means it is proportional to this mass. And again this force is proportional to m2, this mass. Then again this force is inversely proportional to r squared. Clear? This stuff he defined using experiments, okay? Using experiments, okay? So F is proportional to m1, F is proportional to m2, and F is proportional to 1 over r squared. Clear? So he combined them. This was just an experiment. There's no mathematical proof behind that. F is proportional to m1, m2, and r squared. F is proportional to m1, m2 and r squared. Clear? Then he did some further experiments and found this constant, and that constant was g. F equals g m1 m2 over r squared. Clear? F is g m1 m2 over r squared. This g was the proportionality constant, and he identified that this g occurs in many practical scenarios related to gravity. So the given name to this g was universal gravitational constant. Clear? The given name for this g was universal gravitational constant. Clear? Universal gravitational constant. So there, the value of this universal gravitational constant is 6.67, but usually in questions we get this as 6.7. 6.67 into 10 to the power minus 11. 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared. This is Newton's, this is a universal gravitational constant. Clear? So this is one of this is action and the other one is reaction, and the point of action of this force is the center of gravity. Okay, point of action of this force is the center of gravity. Clear? It's acting on the center of gravity. Clear? Okay. So go to exercise 1, question 1 and 2. Exercise 1, question 1, 2 and 3. 1, 2 and 3. So like, how do we know how do we know this part, that the force goes down when R increases? How do we know this? There's no mathematical background or any logical reasoning behind this, okay? Because that's why we call them experimental laws, okay? These are results of experiments, okay? So in experimental laws, we don't have a logic behind why it goes down, why it decreases when R increases, okay? That's how it works. So, exercise 1, question 1, it's simple. If Mali, tute again in the Zoom chat. And I need a tute too. F equals G M1 M2 over R squared. F equals G M1 M2 over R squared. Thank you. So, G is, whenever not given, I would use 6.7 into 10 to the power minus 11. 6.7 into 10 to the power minus 11. M1, M2. M1 is 5 into 10 to the power 6. And other one is 4 into 10 to the power 8. 5 into 10 to the power 6. 4 into 10 to the power 8 over R squared. The distance is 2 meters. Distance is 2 meters, so 2 squared. Distance is 2 meters, which is 2 squared. This is the force, G M1 M2 over R squared. Then the second one, I'm not going to solve them, okay? These are simple questions. Question 2. The gravitational force acting between two objects is F. So, again M1, M2, gravitational force F acting between two objects is F. So, F is G M1 M2 over R squared. What happens if I increase the distance? If I double the distance, then F1 is G M1 M2 over, here I'm going to get 2R squared, which would give me G M1 M2 over R squared. 2 squared means 4. 2 squared means 4. Then I get F over 4. F1 becomes F over 4. F1 becomes F over 4. Okay. So that's how the force works. Clear? Then in the second question, we increase the distance, we double the distance, but multiply one mass by 4. Then what do I get? What do I get? F equals G M1, 1 mass, I'll use 4M2. 4M2. I multiply 1 mass by 4. Then here, R squared, I could use what? I could use 2R squared, right? 2R squared. 2R squared. Then this 2 squared and this 4 will cancel out. This 4 and this 2 squared will cancel out. Then I have G M1 M2 over R squared, which is again F. So in this scenario, this is equal to the initial force, okay? In this scenario, it is equal to the initial force F. F2 equals F. Clear? F2 equals F. In this scenario, F1 equals F over 4. And in the third question, in the third one, you have this one like this. Initially radius of both is r. Initially radius of both objects is r. Initially radius of both objects is r. And the force acting between them, I could tell F. Force between them, F. So F equals G m1 m2 over r squared. So G m1 I could write how? Volume 4 over 3 pi r cube into density. 4 over 3 pi r cube into density. This is m1, right? This is the mass of this guy. 4 over 3 pi r cube, that is the volume into density. Volume into density. And this one has the same mass, right? Both have the same mass. So this squared, right? Both have the same mass. So this into this squared. What is the distance between the center of gravity? It's 2r, right? Distance between center of gravity is 2r. So it is 2r squared. Then in the new scenario, radius of 1 is 2r. Radius of 1 is 2r. And the radius of other one is r. Radius of other one is r. Then what is the force? F equals G. What is the mass of this guy? 4 over 3 pi 2r cube rho. Radius is 2r. Then this one 4 over 3 pi r cube rho. This is radius is r. Then the distance between their center of gravity is 3r. Distance between the center of gravity is 3r. Clear? So you just solve this. Okay. You just solve this. So I'll take this as f1 and let's divide these two. Okay. Let's divide these two. I would write f1 over f. I would write f1 over f. What do I get here? G. When I solve this, I would get 4 over 3 pi r cube into rho squared. 2 cube, I'll take it out. I'll take 2 cube out. G 4 over 3 pi r cube rho 4 over 3 pi r cube rho. This 2 cube, I'll take that out. Then 3 squared r squared. Then here G 4 over 3 pi r cube rho 4 over 3 pi r cube rho squared. Over here, this one I can write 2 squared r squared. This one I can write as 2 squared r squared. Then everything cancels out. Everything cancels out. G 4 over 3 pi r cube. G 4 over 3 pi r cube. R squared and r squared. I'm left with this 2 cube. And this 2 squared, I'll take that up. 2 squared. And this 3 squared. This 3 squared. That's all. This gives me, I think, 32 over 9, right? This gives me 32 over 9. Clear? Okay. Write down if you have to write anything and I'll continue. So the questions are straightforward, okay? Just use the equation, that's all, okay? Just use the equation F equals G m1 m2 over r squared. That's all you have to use, okay? Just use the equation. It changes with mass and radius, mass and distance actually. Mass and the distance between two objects. When I use the term distance between two objects, what I'm actually using is the distance between the center of gravity of two objects, okay? Why do I divide f1 by f? Because I need to find f1 using f, right? That's why now I have f1 of f equals 32 over 9. So now I can write what? If f1 over f is 32 over 9, now f1 is 32 over 9f. F is the given data, right? Clear? F is the given data, okay? F is the given data in the system. So I have to find f1 using f. So to find that, what I could do is I can divide f1 by f, which gives me a numerical value. Then using that, I can find f1. Is that clear? The student who asked the question? Is that clear? Anyone writing this? Anyone still writing this? No? Okay. Okay. So we need to, like, there's a term that we learned, okay? There's a term that we learned which is gravitational field intensity, okay? We learned a term called gravitational field intensity, okay? So what is this gravitational field intensity? The force acting on a unit mass, okay? Force acting on a unit mass, clear? So now we have to, like, convert this to find gravitational field intensities and to have some idea about how gravitational field intensity changes in a given area or around a given mass, okay? So let's start with a system like this. A point mass m, a point mass m. Let's find how the gravitational field intensity changes, okay? Let's try to find how the gravitational field intensity changes uh, around a unit mass, okay? So if I need to find the gravitational field intensity at a distance of r, what I should do? I should place 1 kilogram here, right? I should place 1 kilogram here. Clear? Okay. Now, because gravitational field intensity is the force acting on 1 kilogram, right? Force per unit mass. Clear? Then, usually these gravitational forces are vectors or are attractive forces, and definitely gravitational field intensity is a vector. Why? It has a direction. It's a force, right? Okay. So, usually these gravitational forces are attractive forces. So, this force acts on this direction. Clear? Then what is the value of this force? The force acting on 1 kilogram is gravitational field intensity, okay? Gravitational field intensity is force acting on 1 kilogram. Gravitational field intensity is force acting on 1 kilogram. Then I can write G, this mass is M, this mass is 1 kilogram over R squared. Newton's law of gravitation. G m 1 over r squared. Clear? Then I'm gonna get G m over r squared. Gravitational field intensity is G m over r squared. Clear? So if I convert this into a graph, I need to plot the graph of gravitational field intensity around a mass. So what do I get? What do I get? So as you see, when it is really close to the object, this definitely we have to choose a direction, a positive direction. I'll choose this as my positive direction. So when you place 1 kilogram in this side, the force will be acting on this direction. When you place a 1 kilogram here, the force will be acting in this direction, right? These are attractive forces always, right? Clear? So these are positive. Whatever the forces acting on this side will be positive, and this side will be negative, right? This side will be negative. Why? This is my chosen direction, but the force is acting on the opposite direction, right? Clear? So, and when it comes to this equation, G and M are constant. When R goes to 0, this should shoot up to infinity, right? When R is close to 0, this should go up to infinity, right? When R is 0, this one becomes infinity, right? So when it is really close to this mass, gravitational field intensity is infinity. And when R increases, it decreases and go like this. Okay. It would go like this. Clear? Then in this side, it goes like this. Clear? In this side, it goes like this. Why? It's the same pattern. Okay. Definitely. It's the same pattern, but forces are acting on opposite direction, right? So the same graph, but in negative side. Clear? That's how the gravitational field intensity changes around a point mass. Clear? But knowing the gravitational field intensity around a point mass is useless. Why? There are no actual objects like that, right? Okay, this is clear, right? Nothing complex. Just use the Newton's law of gravitation to find the gravitational field intensity and gravitational field intensity graph. Clear? But like knowing the gravitational field intensity and how it acts around a point mass is useless. Why? We don't find actual objects like this, right? Okay, you can't find actual point mass, right? So let's try to find the gravitational field intensity around much practical objects. And when it comes to practical objects, okay, when it comes to practical objects, like usually many examples or many systems that we discuss when it comes to gravitation are spherical objects, right? Usually when it comes to gravity, like 99.9% of the questions, there will be a most probably a planet, right? And there will be a star, and there will be planets rotating around stars. There will be satellites rotating around planets. So in many scenarios, the center object is a sphere, right? Clear? In many scenarios, in many practical scenarios related to gravity, the center object becomes a sphere, right? Clear? So let's find these gravitational field intensities for a sphere. Okay? Let's find the gravitational field intensities for a sphere. So this is a sphere. This is a spherical object. Now, this is the center of gravity. Let's find the gravitational field intensity at a distance r. Let's find the gravitational field intensity at a distance r. This is the gravitational field intensity at a distance r. Okay. So again, Newton's law of gravitation, you have 1 kilogram here. So when you apply the equation, force will be acting on this direction. So F will be, and the force acting on 1 kilogram is gravitational field intensity. Gravitational field intensity is force acting on 1 kilogram. Gravitational field intensity is the force acting on 1 kilogram, which means G. Center mass, let's take as capital M, Gm. This as 1 kilogram over distance is r, so r squared, which is Gm over r squared. Clear? Gm over r squared. Okay. So when it comes to a point placed outside the spherical object, there's no difference between a point mass and a spherical object. Okay. See, same equation, same everything, right? See. So the answer that I'm getting for a point mass or the answer that I'm getting for a spherical object is same, right? Gm over r squared. Why? What matters is the center of gravity. Clear? That means, see, these particles are a bit closer to this one than r. Clear? These particles are a bit away from the distance r. So when you do the whole calculation, it balances out and gives you the same equation Gm over r squared. Okay, that's why you get the same answer. Okay, clear? That we don't have to prove. Okay, to prove this, you definitely have to integrate. Okay, that we don't have to prove in the syllabus. But what you should understand is what matters is the center of gravity. Okay, what matters is the center of gravity. Clear? So ideally, to find this field intensity, what should you do? You should break this into small particles. You should break this into small particles and calculate the small field intensities here and get the sum. But when you get the sum, you get the same answer. Okay? Why? We can consider that this whole mass is centered to its center of gravity, right? That's the meaning of center of gravity, right? We can consider that this whole mass is shrinked into the center of gravity. That's the whole point of center of gravity, right? Okay. So for a point placed outside from the object, you get the same answer, nothing different. Okay. So if the radius of this spherical object is r, if the radius of this spherical object is capital R, at this point, again the field intensity would be G capital M. Here, not simple r, this distance is capital R, so Gm over capital R squared. Clear? So from infinity to the surface of the object, it's simple. Okay? It's simple. Now comes the complex part. Now, what about the gravitational field intensity acting on a point like this? What about the gravitational field intensity acting on a point like this? That means on a point placed at a distance r, at a point, on a point placed at a distance r, okay? But that r distance is smaller than capital R. That r distance is smaller than capital R. Now what is the gravitational field intensity acting on this point? How can I calculate that? To find this, I have to break the system into two parts, okay? To find the gravitational field intensity acting on this point, okay, I have to break the system into two parts. What are the two parts here? What are the two parts? I'll draw a circle around this, okay? I'll draw a circle around this such that it goes through my required point, and there's a mass around this circle and in this circle, right? There's a mass around this circle and in this circle. Clear? Now, if I do something like this, I'll draw two lines like this. I'll highlight this part situated out of this circle. And I'll highlight this part again situated out from this circle. Clear? Situated out from this circle. Clear? So when you consider these two parts, okay, when you consider these two parts, this side, so what I'm interested in is the force acting on this point, okay? I'm interested on the force acting on this point. That's my gravitational field intensity, right? So this mass will pull this point in this direction, and this highlighted mass will pull this point in this direction. Clear? Then again, okay, then again, this mass is huge than that part, right? This highlighted part is larger than that highlighted part, right? This highlighted part is larger than this highlighted part. Clear? And at the same time, this highlighted part has a higher distance from this point than this one, right? So the equation for the gravitational field intensity is Gm over R squared. Equation for the gravitational field intensity is Gm over R squared. So higher the mass, higher the intensity, higher the mass, higher the radius, or higher the distance, lower the intensity. Clear? So when you consider this part, it has a higher mass but higher distance. Clear? When you consider this part, it has a lower mass but lower distance. Clear? So as a result, if you prove this force and this force actually cancels out, okay? This force and this force, it actually cancels out, okay? They actually cancels out. Clear? Clear? Uh, I mean, you can prove that by integration, okay? The maths paper you can try, okay? Not a big deal, okay? Not a big deal. You can integrate and solve that. You can do an integration and prove that it cancels out, but in our syllabus it's not required. So that means the force acting on that point due to this part and force acting on this point due to this mass, they cancels out, okay? And if you increase this angle, if you keep increasing this angle, it would color the whole surrounding part, right? If you keep increasing this angle, eventually it would color this whole 360 degrees part. It would color everything. Clear? Clear? That means the final idea is that this we can easily prove. We need a bit of mathematics, so we don't have to do that in our syllabus. What you can prove is the mass around this circle have no resultant force, doesn't create any resultant force on this point. Clear? Mass around this circle won't create any resultant force on this point. Clear? So what matters is the circle placed inside. Okay? So what matters is this inside circle. Okay? What matters is this inside circle. Clear? What matters is this part. Okay? And the radius of it is r. Now since it is just another sphere, okay, since it's just another sphere, I can find the field intensity on that surface, okay? I can find the field intensity on that surface easily. How? Gm over r squared. Clear? Since this is another simple sphere, okay, and this is an outside point, right? It's the surface. Surface is an outside point. I can easily write, if the mass of this part is Gm dash, I can write field intensity here is Gm dash over r squared. The surrounding part have no resultant impact on this. Clear? But I can find m dash easily. How? Overall mass of this object, is capital M, right? It is for a volume of 4 over 3 pi capital R cube. Clear? This M was for a volume of 4 over 3 pi capital R cube, right? But this inside volume is 4 over 3 pi simple R cube, right? This inside volume is 4 over 3 pi simple R cube. Clear? Then I'm going to get M simple R cube over capital R cube. Clear? M simple R cube over capital R cube. That is M dash, right? Clear? So I can find M dash, this inside mass. Clear? So I can find G over R squared. I can write M R cube over capital R cube. Then I'm going to get G M over capital R cube into simple R. Why? This one and R cube cancels out. Then I'm left with simple R. Clear? So I have Gm over capital R cube into simple R. Now see, when you see this equation, you should understand that this is an y equals mx graph, right? Why? G, m and capital R are constants, right? G, m and capital R are constants. Clear? Everything is a constant. G, m, capital R, everything is a constant. Clear? So simple R is the only variable, right? Simple R is the only variable in this case. Clear? So it's a y equals mx graph, right? It's a y equals mx graph. Okay? So uh, if I draw the graph for the whole object, field intensity, if I choose this as the positive direction, the graph I would get is like this. Outside this sphere, it is just gm over r squared, right? Outside the sphere, it's gm over r squared. So it would go like this, and in this side it would go like this. Clear? But inside, okay, but inside, I'll draw this line later. But inside, it's a y equals mx graph, right? Inside the sphere, this is how it changes with r, right? Clear? It's a y equals mx graph inside the sphere, right? So it goes like this. Clear? So it goes like this. Okay? And this is field intensity. Okay? Got the idea? Got the idea? That's how field intensity changes with the distance. Clear? Okay? So inside the sphere, it's a y equals mx graph. Outside the sphere, it's just an inverse proportional graph. Clear? So I mean everything is included in the tube, but you have to write, if you have to write down anything, write down try exercise 1 question 6. Try exercise 1 question 6. So the whole graphs and everything is included in the tute, but check the tute and do any, if you need to do any changes, try to do them. Yes, there's a request to explain the graph again. I'll do that again. You can write down anything and ask any questions if you have, and I'll explain the graph again. multitude WhatsApp group. Put the tudes into the WhatsApp group. And like students are joining through like YouTube or anything, they can get the tute from the WhatsApp group, okay? And I think it was there, okay, it is already there, the tute is already there in the WhatsApp group, but you can find that again. And if you need to join the group, or if you need to get the tutes delivered, or if you need to like receive the, like if you need to join the classes or anything, just contact this number, or to request for the tutes, not 70-154-6825, not 70-154-6825. Contact this number. I'll explain this one again until others are trying the question. So here what is happening is, outside the sphere it's quite simple, okay, it's just like a point mass. But when it comes to the into the circle, what happens is the affecting mass decreases. So as a result, the equation changes. But when I try to create an equation for this, okay, when I try to create an equation for this, what I get is this one. That means what I'm going to get is, if I draw a circle through the point that I'm interested in, I can prove that all the mass placed out of that circle have no effect on this particle, because all the surrounding forces cancel out each other. As a result, I'm left with this internal part m dash. So when you consider this internal sphere, it's just another sphere, and we know the field intensity on the surface of a sphere is gm over r squared. And in this case, it is not m, it is m dash. Only the mass inside the circle. Clear? So I can find m dash how? If for a volume of 4 over 3 pi capital R cube, you have a mass m. What is the mass for 4 over 3 pi simple R cube? Then I get capital M R cube over simple R cube. Then they cancels out. And I'm going to get gm over capital R cube into simple R. This is a y equals mx graph. Clear? This is a y equals mx graph. So inside the sphere, how it changes is, it changes as a y equals mx graph. Y equals mx graph. Okay? Clear? The student who asked the question? Because it's a linear relationship with R inside the sphere. Only variable is simple R. That's why. Then one more thing. Pay attention, everyone. One more thing. Pay attention. One more thing. If we take a shell, what do we get? That means if I consider a small shell like this, that means there's no mass inside, it's empty. There's no mass inside, it's empty. It's just a shell. Clear? Then what would be it's just a very thin shell. Just a very thin shell. A very thin shell like this. What would be the gravitational field intensity of this object? It would be like this. This and this. Because outside the sphere, it's still gm over r squared. Why? Still the center of gravity is at the middle, right? Still for the whole shell, center of gravity is at the middle, right? So for the whole shell, still the gravitational field intensity here is gm over r squared. Clear? It's still gm over r squared. Okay? But inside the sphere, it's going to fall to 0, right? Inside the sphere, it's going to fall to 0. Why? Why? Outside the sphere, it's going to act as gm over r squared. Why? There's no difference between a point mass here or a object having the center of gravity here. So I'm going to get the same equation as gm over r squared. Clear? But when it comes to an internal point, again that same scenario happens. Force acting from this mass will cancel out the force acting by this mass. Clear? Force acting by this mass will cancel out the force acting by this part. And in this scenario, there's no internal mass. It's a shell. So there's no mass inside the sphere, right? In this case, there's no internal mass to create a force, right? There's no internal mass to create a force. So there's no internal gravitational field intensity. Clear? So in this case, the gravitational field intensity inside this is 0. Okay? Now, the gravitational field intensity inside this is going to be 0 in a system like this. Okay? Continue to the question. Exercise 1, question 6. Exercise 1, question 6. Question 17. Question 18. 6, 17, 18. Try these questions quickly. In question 17, it's not the mass of the object, it should be the weight of the object, okay? In question 17, it should be changed to the weight of the object. Well, put it in the Zoom chat. I'll put the tunes again in the Zoom chat. Uh, so the gravitational attraction between these two is in this direction, and gravitational attraction between these two is in this direction. Both are attractive forces, right? Both are attractive forces, and these two should be equal. Why? 6.4 and 6.4. We need to find the acceleration of this guy, right? We need to find the acceleration of this guy. So what I can do is, I can find this force F. This force F will be G simple M. I'll take this as capital M over, if this is 8 and this is 6, this should be 10, right? It's a Pythagoras combination, 8, 6 and 10 over 10 squared. Over 10 squared, it is 10 into 10 to the power minus 2 because it is centimeters. So 10 into 10 to the power minus 2 squared. G capital M simple M over 10 into 10 to the power minus 2 squared. That is the force acting between these two. That is the force acting between these two. And these two forces are equal. Why? It's the same mass. But when you consider these two forces, horizontal components of these two forces will cancel out, and only the vertical components would matter at the end, right? Why? You have two equal forces and horizontal components will cancel out, right? Clear? Because they are in opposite direction. Only the vertical components would matter. Clear? So what actually matters is the overall force acting on this object would be overall force acting F equivalent. Acting on that object would be F. F is this. G capital M simple M over R squared 10 into 10 to the power minus 2. And I have to get cos alpha here. If this is alpha, I have to get cos alpha, right? Clear? To get the component in this direction, I have to get cos alpha. Cos alpha is 6 over 10, right? Cos alpha is 6 over 10. Okay? I have to get cos alpha to get the component in this direction. And since this is a triangle, if this is alpha, cos alpha is 6 over 10. Cos alpha is 6 over 10. And again, you have to multiply this by 2. Why? There are two forces, right? From both sides. So this is the resultant force. So using this resultant force, I can apply what? I can apply F equals ma, right? I can apply F equals ma. F equals ma. I can apply F equals ma. Clear? Then I can write F equivalent equals ma F equivalent equals ma, then m cancels out, and the acceleration become F equals ma, then this simple m and this simple m cancels out. Then I'm left with g. G means 6.7 into 10 to the power minus 11. Capital M is this guy, 6.4 kilograms. Simple m cancels out. That means 0.01 gram cancels out because it's in both sides. And you have 6 over 10, 6 over 10 and 2 over, you have this one. Sorry, it squared, right? It squared. 10 into 10 to the power minus 2 squared. This is the acceleration. Okay. This is the acceleration acting on the object. You have to solve this, okay? You have to solve this and get the answer. Have to solve this and get the answer. So here what we are trying to find is equivalent gravitational force, okay? And there's another term called, pay attention, there's another term called equivalent gravitational field intensity. Equivalent gravitational field intensity is if there are different field intensities acting on the same point, the vector sum of these gravitational field intensities is the equivalent gravitational field intensity, okay? Or resultant gravitational field intensity, equivalent gravitational field intensity or resultant gravitational field intensity is the overall gravitational field intensity. That means you just have to get the vector sum of all the gravitational field intensities acting on a point. Okay. Then at the same time, there's something called neutral points. Neutral points. What are neutral points? Neutral points are in a system as a result of multiple gravitational field intensities. At some points, resultant gravitational field intensity would be 0, okay? At some point, as a result of multiple gravitational field intensities, the resultant gravitational field intensity would be 0. Such points, we call them neutral points, okay? If they ask you to find neutral points, that's what you have to do, okay? Write this down. And what is the next question number I asked you to try? 17. And if you're done with 17 and 18, go to 19 and 22. If you're done with 17 and 18, go to 19 and 20. So what I did was I found the force act between them, then got the cos component downwards, multiply by 2. Why? There are two components. That's how I got the resultant force. Then for the resultant force, I applied F equals ma. Then I got the resultant acceleration. Clear? Question 17. The weight of an object on Earth is 200 newtons. If the radius of the Earth is r, what is the mass of the object it should be weight. Okay, I asked you to change it to weight. What should be the weight of the object at a distance 2r from the center of the Earth? At what distance does the object weight is 100 newtons? Anyone writing this? Anyone? Okay. So question 17. Question 17. Radius is r. So on the surface of Earth, weight is 200 newtons. So what is the meaning of this 200 newtons? 200 newtons means m into gravitational field intensity, right? ME. Clear? That means this 200 newtons is the gravitational pull. This 200 newtons is the gravitational pull. That means G, if this is simple m and this is capital M, G, capital M, simple M, and to the distance to this object is r. It's on the surface of Earth. So r squared. Now they are asking what is the weight of that object at a distance 2r from the center of Earth. So now we are considering a point and we keep the same mass at a distance of 2r from the center. So the new weight would be G, again capital M, simple M, over this distance is 2r. This distance is 2r. Then I'm going to divide them. W over 200. W over 200. W is this G, capital M, simple M over 2r squared over this is G, capital M, simple M over r squared. Then W over 200 equals 1 over 4. Everything else cancels out. W is 50 newtons. W is 50 newtons. Clear? These are very straightforward questions. Okay, I'm not going to do the second part. You can find the distance to the object when weight is 100. Okay, just r is changing, that's all. Okay, r is changing. When r changes, gravitational pull changes, and the gravitational pull is what we discuss as the gravitational pull is what we discuss as the uh, weight. Okay, gravitational pull is the weight. Gravitational pull is the weight. Question 18. A man can jump 2 meters above the earth. How high can he jump on the surface of moon? So how it behaves is like this. Okay. How it behaves is like this. Definitely gravitational acceleration decreases or gravitational acceleration changes with the height. Okay. Definitely gravitational acceleration changes with the height. Okay. But in a scenario like this, we can consider it as a constant. Okay. Why? In a scenario like this, we can consider it as a constant. Why? When a man jumps, it doesn't create a huge height difference, right? When a man jumps, okay, when a man jumps, it won't create a huge height difference. It would be a small height difference, clear? It would be a small height difference when a man jumps. So in a small height difference like that, the gravitational field intensity or the gravitational acceleration won't change much. Clear? In a very small height difference like that, the gravitational acceleration won't change much. Okay? So as a result, here you can directly use MGH. You can directly use MGH, potential energy. That means when a person jumps, okay, when a person jumps, he creates a certain kinetic energy, right? That kinetic energy he creates when he jump is same on moon and earth, right? He creates that kinetic energy using its chemical energy, and the chemical energy he can produce is same, right? Whether it's moon or earth. So in both scenarios, the kinetic energy this man produce, okay, the kinetic energy this man produce is same. Okay? In both scenarios, the kinetic energy this man produce is same. Okay? But so when he reached to the maximum height, okay, when he reached to the maximum height, potential energy is mgh, and this kinetic energy converts into that potential energy which is mgh, right? This kinetic energy converts into the potential energy which is mgh. Clear? So when you consider that mgh, okay, when you consider that mgh, that potential energy is same for earth and moon, okay? Potential energy is same for earth and moon. Why? Because the produced kinetic energy is same. So when he reached to the maximum height, that kinetic energy converts into potential energy. So in both scenarios, the potential energy should be same. But in both scenarios, G changes. So with G, H changes, right? Clear? So here it's M. G is 10. On Earth, G is 10. And the person can jump a distance of 2 meters. The person can jump a distance of 2 meters. Here, M, and the gravitational acceleration is 1.7 into h dash. So M cancels out, then h dash is, M cancels out, and h dash is 20 over 1.7, which is 11.76 meters. 11.76 meters. Clear? This height would be 11.76 meters. So next, before moving forward, what I have to do is I have to teach that motion of a planet around sun part 2. Should we get the interval and do that, or should we do the motion of a planet and get the interval? Would take at least 20 minutes to finish motion of a satellite and a planet. What should we do? Huh? We need the interval or not? We didn't do much, right? So can I continue? Looks like no. Okay. Then let's do it this way. Try to finish question 19, 20, 19, 20, and 9. Try question 19, 20, and 9. I'll finish these questions and start the motion of a planet and a satellite after the interval. So time is 57. I'll start around maybe 5:15. I'll start around 5:15. Be here on time and finish these questions. Then let's move to the next part, the motion of a planet and a motion of a satellite. Quickly try to finish the questions. Question 19. Question 19. The radius of a planet shown in figure is r, and the radius of a spherical cavity inside is simple r. What is the gravitational field intensity at P at a distance L from the center? The cavity starts at a distance L from the center of the sphere. So there's a sphere like this, and there's a cavity inside. So I would do something like this. I would take a full sphere. I would take a full sphere, and this is the center. I would take a full sphere, and this is the center. And this is P. And this gap is L. This gap is L. Then I can find the gravitational field intensity here, E1, from this whole sphere. What is the gravitational field intensity acting on this point by the full sphere? What is the field intensity, E1? Gravitational field intensity is G m over r squared, which means G uh, radius of the planet is r. Radius of the planet is r, so G 4 over 3 pi r cube, 4 over 3 pi r cube, and density is d. So this is the mass, right? Volume into density. Volume 4 over 3 pi r cube into density. 4 over 3 pi r cube into density. Gm over r squared. What is r? R is the distance between this center and this one, which is capital L. Then I'm going to get capital L squared. Capital L squared. Now, this is not the actual system, right? This is not the actual system. There's a cavity in the system, right? Yeah. This is not the actual system. There's a cavity in this. Okay. So, what I could do is, so since there's a cavity like this, okay, since there's a cavity like this, what I'm going to do is I'm going to find the gravitational field intensity that could be created by a spherical object of this size. Okay. What I'm going to do is I'm going to find the gravitational field intensity that can be created using a spherical object like this. Clear? How can I find that? Again, Gm over r squared, which means G, what is the volume of this? What is the volume of this part? 4 over 3 pi. The radius here is simple r cube into density. This is the volume of a spherical object like this into density. This is the mass of this spherical object over this distance between this center and this point is capital L minus simple L, right? Why? This is simple L. This distance is simple L. If that is simple L and if this is capital L, this distance is capital L minus simple L. So G m over r squared, r is the distance between this point and this point, which is capital L minus simple L squared. Capital L minus simple L squared. Clear? Now what can I do? Now what can I do? Now What I need is the gravitational field intensity created by the object with the cavity. It is equal to the gravitational field intensity by the full object minus gravitational field intensity by the small object, right? This difference will give me the gravitational field intensity created by a object of this shape, right? Okay. So instead of trying to work with the object with the cavity, what I did was I consider these two as two separate spheres and got the field intensity created by the full sphere, and I'm going to subtract the field intensity created by a small sphere like this, which is equal to the field intensity created by the object with the cavity, right? Clear? That difference gives me sufficient information, right? Huh. So E1 minus E2 would give me the answer, which is E1 is this, G 4 over 3 pi capital R cube D over L squared minus G 4 over 3 pi simple R cube into D over again capital L minus simple L squared. This is the answer. You don't have to solve this. This is the answer. Okay. And question 20 I'm not gonna do because it would give the it's the same method. Okay. Question 20 is you have to do the same thing. Okay. Just for two spheres. That's all. Okay. So instead of searching for the gravitational field intensity created by a object of this shape, what I could do is get a full sphere, get the small sphere, and subtract the gravitational field intensities. Clear? Subtract the gravitational field intensities. Quickly write down. I'll go to question 9 and move further. Question 9. Question 9. Two objects of M and 3M. Two objects of M and 3M are placed at a distance d. What is the distance from the object of mass m to the resultant gravitational field intensity due to the two object is 0. So the gap is d, and there's a neutral point in between. There's a neutral point in between. Let's take the distance to the neutral point as x. Then if this is x, this is d minus x. And for this to be the neutral point, gravitational field intensity by this object on here and the gravitational field intensity by this object on this point should be cancelled out, right? Clear? They should cancel out, right? That means the gravitational field intensity by this object is g simple m over, what is the distance? X squared. And gravitational field intensity by this object would be g 3m over d minus x squared, right? G simple m over x squared. This is g 3m over d minus x squared. And you can solve this for x, right? That's all. Okay? You can solve this and get the value for x. Gravitational field intensity by this object and gravitational field intensity by this object. Then g and m cancels out. I'll get the square root 1 over x equals here root 3 over d minus x cross multiply d minus x equals root 3x, then x equals d over 1 plus root 3. X equals d over 1 plus root 3. D over 1 plus root 3. Okay, I'll move further. Quickly write this down. Quickly finish writing. Now we have a lot of theory to learn after this point. We are still getting to know the terms, okay? This is not the actual applications of gravitational field and gravitational field intensity. Now only we are going to discuss the actual applications, such as the motion of a satellite, motion of a planet, things like that. Okay. Next. Anyone? Writing? Anyone? Done, right? Everyone? Okay. So let's move forward. The next application is, okay, now only we are going to discuss actual applications of gravitational fields. So we all know that this whole systems, okay, all these systems, like gravitational systems in the sense, things like planetary systems and our communication system with satellites and all, everything is a result of gravity, right? Everything is a result of gravity. Satellites are there due to gravity, and planets are there due to gravity. Okay, so everything is there due to gravity. Okay, everything's there due to gravity. So now I'll discuss both these scenarios using the same concepts. That means, take, if this is sun, let's take the mass as m, and if this is a planet, if it is simple m, it's going around the sun due to gravity, okay? It's there due to gravity. And the same scenario for the planet and satellite too, right? Just like like Earth is going around the sun, satellites go around the planet, right? Okay, so it's the same thing. Okay, so in the syllabus they are teaching it, they have placed these two content at two different places, but it's the same. Okay, it's the same. So why do they rotate? Why do planets have to rotate? Why can't they stay there? Why do planets have to rotate around sun? Why can't they just stay there? Why can't they just stay there? Yes. Why? Uh, Definitely, due to the sun, there's a gravitational pull on the mass, right? Due to sun, there's a gravitational pull on this mass. Clear? If there's a gravitational pull on this mass, okay, if it is there stationary, it would be pulled by sun, right? Clear? It would be dragged by sun towards it, right? Clear? If it is there, gravitational pull would force it towards the sun, right? So we have to use this gravitational force for something else to make sure that we won't go towards the sun. So we use this gravitational force for something else. What is that? We use it as the centripetal force and we go around. We use it as the centripetal force and we go around the system. Clear? Clear? Okay. And there was someone asked me the question like, how do the planets know the exact velocity that you should go to stay on this system? It's a very, it's a very crucial question actually. Still they are working on it. Okay, still they are working on it. There should be a perfect velocity to balance out the gravitational force. If that velocity changes a bit, the orbit may change and the system would collapse. But everything is perfect at the moment, okay? Everything is perfect. It is because, it's not like the sun was there and the planet was there and we kept the planet and gave a velocity. It was just a bunch of particles rotating around after a blast, right? After a huge blast, it was just a bunch of particles rotating. So with time, some particles got together and formed planets. So all those particles that were involved in creating that planet had the same proper velocity to be in that orbit. So for you to be in a certain orbit, you should have a proper velocity, right? You should have a proper velocity. So what happened was, it was just a bunch of particles rotating, random particles, billions of particles rotating after a blast. But things were close to each other. Particles that were close to each other were compressed and somehow they created planets, right? So when the planets were created, all the particles were involved in that had the velocity, okay, required velocity. So they just remained in the system, okay? They just remained in the system. It's not like planets were placed there and given a velocity. It's not like that, right? Okay. For the satellite, yes, we do that. For the satellite, we place the satellite at the correct position. We use thrusters and give the proper velocity. Okay. Okay. So if I do a calculation for this, okay, what is the force between these two? Gravitational force is G capital M simple M over R squared, right? G capital M simple M over R squared. Okay. Then this gravitational force is balanced out using a centripetal force, right? This gravitational force is balanced using a centripetal force, right? Clear? So R cancels out, M cancels out. So V equals root Gm over R. So to be in this orbit, this planet must continue to move with this velocity, okay? If the velocity changes, orbit must change, okay? If the velocity changes, orbit would change, okay? So this is the velocity that this planet should have to go around the sun in this orbit, okay? And the mass of the planet have nothing to do here, see? Simple m cancels out, simple m cancels out, so mass of the planet have nothing to do here. It's just the mass of the central object. So that's why when it comes to satellites, we have smaller satellites. Actually, we have very small satellites like this, okay? there are very small satellites of this size. Okay, there are some satellites of this size, and also there are satellites like closer to a football field. Okay, for an example, the James Webb Telescope is a satellite actually. James Webb Telescope, it has a sun shield. It has a sun shield of the size of around half of a football field. Okay, so size of the satellite doesn't matter. Why? Simple m is not there in the equation. See, simple m is not there in the equation. It cancels out. Okay, so whatever the size of the object with the proper velocity, you can place it on the proper orbit. Okay, whatever the size of the object, whatever the mass of the object, you can place it on the correct orbit using the correct velocity. Okay, so now again, if I have to find the periodic time of a full circle, that means in our language 1 year. 1 year means time it takes by the planet to go a full circle, right? Clear? 1 year means the time it takes by the planet to continue a full circle. Or the periodic time, right? Periodic time is round time for a full circle. Clear? Periodic time, I can, if periodic time is t, I can write v equals 2 pi r over t, right? V equals 2 pi r over t, right? Length of full circle is 2 pi r. If the time for the full circle is t, 2 pi r over t gives me the velocity of this planet, right? So v equals 2 pi r over t and v equals root gm over r. Root gm over r. Then what do I get? T equals 2 pi r. I'll take t here and these guys here. R over gm. This gives me 2 pi square root. I'll take this one here, r cube over gm. R cube over gm. So this is the periodic time or the time of 1 year of a planet. Okay. Everything is included in the tute. Okay. You just do a few, maybe just check whether it's everything is correct. If you have to change anything, do some changes, but you don't have to write. Everything is included in the tute. Then, then like again, there's a relationship like this. Okay. Take this guy. Take this guy. T equals 2 pi r cube over gm. I get the square of both sides, okay? I get the square of both sides. T squared equals 4 pi squared over gm into r cube. 4 pi squared over gm into r cube. So as you see, this part is a constant, right? For a given planet, g is a constant, m is the mass of the planet is a constant, everything is a constant, right? For a given planet, this part is a constant, okay? So you can tell that t squared equals r cube. This we already know, okay? We don't have to define an equation and this proportionality separately because anyone who know the equation would know this, okay? Anyone who know this equation would know this. T squared is proportional to r cube. The reason for me to write this separately is there's a name for this law called Kepler's law. Why this is important is these laws, some of these laws like Kepler's law were invented way before we invented everything about gravity, okay? They knew some stuff, okay? They knew some stuff. So some laws, there are some laws, these laws were invented way before than we invented all these equations, okay? Okay, so this we call Kepler's law. You can use them directly if you need, okay? So that's the story here. And I'll extend this concept a bit to a satellite too, okay? I'll extend, I mean, I'm just going here and there, so I'm not going through the correct path. But we'll see how the time permits. Yeah, but anyways, I'll do this part and move to satellites. Let's do it that way. So is this clear? Everything clear up to this point? Yes? Any questions? Any questions? Okay. Go to exercise 2, question 4. Go to exercise 2, question 4. Go to exercise 2, question 4. So even in this question, I think the reason for me to give this question is I needed you to try that. Calculate the mean radius of moon's orbit around the Earth using the following data. Okay, you can use the data given. The radius of the Earth, definitely you can, so do the question only using the data given in the question. Okay, the radius of the Earth is 6.37 into 10 to the power 6. The acceleration of gravity on Earth is 9.81. And the time it takes for the moon to make one revolution around the Earth is 27.3 days. 27.3 days. Uh, Earth's surface is and the time it takes for the moon to make one revolution around Earth is 27.3 days. So what they need us to find is the mean radius of moon's orbit. Okay. So if you try to do the question, I think you may find that we don't have enough data in the question. Why? We can directly use this equation. T equals 2 pi r cube over gm. Okay. So T is periodic time of moon, which is 27.3 days. Which is 27.3 days. Days means 24 hours for an hour, 3600 seconds. Equals 2 pi r cube over gm. So in this scenario, G is not given, M is not given, right? Both G and M is not given. Okay. G and M is not given, and like the problem is G, if not given, we can use, right? 6.7 into 10 to the power minus 11. But we can't remember everything, okay? If we have to use M, they should give M, okay? Clear? If we have to use M, they should definitely give M, okay? But then, in many questions, you would see this scenario that they won't give this G and M sometimes. What is the reason? You could recreate this information using another, right? How? Assume we all know the gravitational acceleration close to Earth. What is the gravitational acceleration close to Earth? 10, right? 10, or if we try to be more accurate, 9.81. That is something we know, right? I'll use the symbol G for that, okay? I'll use the symbol G for that. Symbol G equals 10, okay? 10 or 9.81, okay? And if I know the radius of Earth, okay? Can you remember gravitational acceleration equals gravitational field intensity at that point? Can you remember? Gravitational acceleration equals gravitational field intensity at that point. Clear? Then gravitational intensity is G capital M over R squared, right? G capital M over R squared, and R is the radius of Earth, right? G capital M over R squared, and R is the radius of Earth, right? Clear? Then using this, I can use G equals Gm over R squared, and Gm equals GR squared. Instead of Gm, I can always use GR squared in questions, okay? Because G is something we already know, 10. 10. G is something we already know, it is 10. Capital R is the radius of this planet. Okay? Capital R is the radius of this planet. Okay? So, and in this, usually you definitely have to use 10 for G, okay? But only if they give that G is not 10, it is 9.81, use that. Otherwise, always use 10, okay? So in this question, they have given us gravitational acceleration around Earth is 9.81. So I can use here 2 pi r cube over gm. Instead of gm, I can use gr squared. G is 9.81. G is 9.81. Capital R is, it is the radius of Earth. Radius of Earth is 6.37 into 10 to the power 6. 6.37 into 10 to the power 6 squared. Gm equals gr squared. Now only unknown in this equation is r. You can solve this and find r, okay? Only unknown in this equation is simple r. You can solve this and find r. Solve this and find r. Okay. So I think it's better if I can yeah. So can we do it this way? I'm gonna, in the English medium tute, I'm gonna skip page 10. Okay. Can someone remind me next week that I skipped page 10? Okay. Sure? Sure? Okay. Sure? Okay. Remind me that I skipped page 10 because I'm gonna skip one page and do a significant part related to satellites. Okay. So that you can do more questions. Okay. So I'm going to quickly go through a certain set of theory points and I'm going to skip content in page 10. Okay. Can everyone remember? Okay. I hope someone will remind me. Okay. Okay. Sure. Okay. So I'm going to skip page 10 and let's go to the satellites part, because since I did satellites just now, because it is equal to the motion of a, because it is almost equal to the motion of a planet, it's convenient to do satellite here. So pay attention everyone, because I don't have to write everything again, see? There's no difference between a planet and a satellite, that's why. Okay? Just like a satellite goes around, just like a planet goes around sun, a satellite goes around Earth, right? When it comes to a satellite, this capital M is our Earth. This simple M is the satellite which is going around the Earth. Clear? So all these equations are valid. Okay? All these equations are valid. So we should provide a velocity equal to gm over r to make sure that this satellite goes around this orbit. Okay. And I can do a small thing like this. Okay. I would change this equation with, sometimes you may have to learn this equation like this. That's why. V, velocity of the satellite is root gm over r. Velocity of the satellite is root gm over r. Okay. Then I could find the gravitational acceleration here, g dash. What is the gravitational acceleration here? What is g dash? G dash is g capital M over r squared, right? G capital M over r squared, right? Because gravitational acceleration equals gravitational field intensity. Gravitational acceleration equals gravitational field intensity. So g dash equals g capital M over r squared. So I can write here. So in this case, this g dash is not 10, okay? It's the gravitational acceleration on this orbit. Clear? Because the issue is in the tube, we use simple g for everything, because that is the standard notation for gravitational acceleration. It is not 10, okay? Gravitational acceleration is 10 only when it is close to Earth, okay? So here it's just the gravitational acceleration on that orbit, okay? Don't mix things up, okay? It's not 10, clear? So here gm equals g dash r squared. Here gm equals g dash r squared. So I'm going to get here gm equals g dash r squared, here r. Then r to r cancels out. I'm left with g dash r. G dash r. Clear? It is g dash r. Just something like this. This part is not actually included in the syllabus, but I would teach this. I mean, I'm not going to prove this or anything, but I would mention this because it would like get rid of some confusions. Like this. We know that we are actually not going in a circular path around sun, right? What is that? Is that ellipse or a parabola? It can't be a parabola, then we won't. It can be a parabola. There are some situations like this. So it's like this. We are going in a ellipse, right? Yeah. So elliptical orbit, right? So many satellites, there are some satellites that go in a circular path. There are some satellites that go in a elliptical path. There are some satellites that go in a parabolic path. Okay? All these scenarios are very natural things. Okay? These are very natural behaviors. Only thing is we can't understand it because we don't know the equation and the proof of a parabola or a elliptical orbit. Okay? But just know this. Now, if this velocity is root g dash r, it will go in a circular orbit, okay? It will go in a perfectly circular orbit. If this velocity is between, this is also included in your tute, g dash r and root 2g dash r, then this will move in a elliptical orbit. If this velocity is equal to root 2 g dash r, it will move in a parabola. Okay, then it would be a trajectory. Okay, trajectory of a parabolic shape. Clear? So just know we have proofs for all these scenarios. Only thing is we only know how to prove the circular scenario. Okay, just like there's a certain velocity go in a circular path, there's a certain velocity to go in elliptical path. There's a certain velocity to go in a parabolic path. Okay. there's always a certain velocity to go in different paths. Okay, clear? So even when we are going to a higher orbit, we use all these. Why? If this is our planet, assume that you have to go to an orbit like this, huge orbit like this. Assume that you have to go to a huge orbit like this. Okay. So when you're going in a huge orbit like this, to take a satellite from here to here or to take a rocket from here to here, it takes a lot of energy. Okay, it takes a lot of energy to go from here to here. So what we usually do is we go for a smaller orbit. We go for a small orbit, circular orbit. Okay, and when we are moving in that orbit, at a proper point, we change the velocity suddenly. We change the velocity suddenly such that we can go in elliptical orbit. Then when you change the velocity here, due to that change of velocity, the path shifts to a elliptic orbit. Path shifts to a elliptic orbit, so it continues in a elliptic orbit. Clear? Then at this point, we change the velocity again and shift to this circular orbit. If we don't change the velocity here, we will continue in the elliptic orbit. But again at this point, we change the velocity to the appropriate value, then we would move to the circular orbit and we will be forever moving in that circular orbit. Okay. What is best here is we need energy to go from here to here. We don't energy to go in this path. Why? It's a gravitational system, right? In a gravitational system, our planet don't have engines, right? It's just a gravitational system, so we don't need energy to move in a gravitational path, right? Then again to go in this elliptical orbit, we don't need a separate energy. We don't need separate energy. Clear? So in this scenario, when we do it like this, we only need energy to go from here to here, then to change the velocity here, then to change the velocity here. Okay, this is far more energy efficient than going in a huge long path like this through the atmosphere. Okay, to go in a path like that through the atmosphere, to a long path like that through the atmosphere, it consumes a lot of energy which a rocket or a satellite system can't easily carry. Okay, so that's how things work. Okay, otherwise you may ask the question, I mean, we know that this moves in elliptical orbits, many scenarios, right? It's just another mathematical relationship like in a circle. The only thing is we can't analyze that because in our syllabus we don't have that proof. Okay, but just know that you don't have to remember these things. Root 2 GR, root GR, you don't have to remember these things. Just know that there are such scenarios. Okay, but sometimes there may be at least MCQs. Okay, sometimes there may be MCQs or maybe essay. Okay, or maybe essay uh, like related to elliptical orbits. Related to elliptical orbits. If such a situation occurs, how can we manage that? There are few equations that we can apply for elliptical orbit. Things that we know. What are the things that we know that we can apply for an elliptical orbit? One is energy conservation. Okay. One is energy conservation. I'm just giving you some hints on how to do questions. Okay. If it is an elliptical orbit, you can't use F equals mv squared over r. Okay. You can't use F equals mv squared over r. Clear? Why? It's not circular. But assume you know the velocity here v1, and if the mass of the satellite is m, and assume if this distance is r1 and if this distance is r2, if this is mass, if you need to find the velocity here, what can I do? What can you do in a scenario like this? So in scenarios like this, okay, in scenarios like this, like one thing is you can apply energy conservation. Potential energy plus kinetic energy here equals potential energy plus kinetic energy here. You can't write the potential energy yet because you don't know the equation for gravitational potential energy. It is not mgh anymore, okay? Gravitational potential energy is not mgh anymore. Next, we will learn the equation for gravitational potential energy. So when you know the gravitational potential energy, then you can apply energy conservation to this point and this point, okay? Kinetic energy plus potential energy equals a constant, okay? Then at the same time, okay, at the same time, I can apply momentum conservation, angular momentum conservation. Why? No one creates an external torque on this system, right? No one creates an external torque on this system. Clear? So as a result, what is the angular momentum? What is the linear momentum here? mv1. We know that linear angular momentum equals moment of linear momentum, right? Angular momentum equals moment of linear momentum. So this is the linear momentum mv1. I multiply it by r1. This gives me angular momentum, right? Then here, this is mv2, and to convert it into angular momentum, r2. So this is angular momentum conservation. So if you get a question like this, okay? If you get a question like this, okay, you can apply angular momentum conservation and energy conservation, and you can do a lot using that, because we can't write the equation for a elliptical orbit. There are separate physics relationships related to elliptical orbits. Usually elliptical orbit is a system with two centers, okay? Elliptical orbit is a system with two centers. So in our physics syllabus we can't analyze that, but if we get a question, there are some stuff that we can do. One is applying energy conservation, and other one is applying momentum conservation, angular momentum conservation. Clear? And Kepler's law also you can't use, okay? Kepler's law, t squared equals r cube, t squared proportion to r cube. This stuff works only for what? For circular orbits, okay? These equations works only for circular orbits, okay? Then one thing to mention, in some questions you would see some terms like, so from this one we should understand when it comes to circular orbit, to have a certain periodic time you must have a certain radius, right? To have a certain periodic time you must have a certain radius. That means based on your radius your periodic time changes. So when it comes to satellite, like weather satellites, when it comes to weather satellites, they move really fast around Earth. So to capture data, they usually go around 7 rounds per day. Okay? They orbit around Earth usually like 6, 7 times or 5, 6 times per day. Satellite, like weather satellites go around Earth. But when it comes to communication, even now the communication satellites are a bit different due to Starlink. Otherwise, from our Arthur C. Clarke model, okay, Arthur C. Clarke is the one who said that you can use 3 satellites and cover the whole Earth, okay? So in our Arthur C. Clarke model, that means the previous models that we use for communication, we have stationary ground antennas. That means if you have an antenna like this, that means we are expecting to have a satellite here. And that satellite should be there forever. Otherwise, this ground antenna, this directional antenna would not be able to communicate with that. It would not be able to communicate with this satellite. Okay. So when it comes to like previous generation of communication satellites, they should be always above a certain point on Earth. Okay. They should be always above a certain point on Earth. Why? All the directional antennas on ground antennas are focusing a certain point. If the satellite is not there, then we are in trouble. Nowadays, everything is different, okay? Nowadays, you have like thousands, not thousands, like 10,000s of Starlink satellites rotating everywhere. So now we have satellite configuration systems. We miss one satellite, we we move to the next satellite, we move to the next satellite, we move to the next satellite. So now the antennas keep shifting between satellites. Now it's a very complex scenario, okay? But when it comes to conventional satellite model, a satellite must be there, okay? So it should be always above a certain point on Earth. We call these kind of satellites geostationary satellites. They are stationary relative to Earth. So what should be the periodic time of this guy? 24 hours. Why? 24 hours. Why? Earth takes 24 hours to rotate a full circle. So if this guy must be above Earth, it should be rotating in a 24-hour cycle, right? So things in the geostationary orbit, their periodic time is 24 hours, okay? For the things on the geostationary orbit, their periodic time is 24 hours, okay? And usually this geostationary orbit is around 36,000 kilometers above Earth, okay? Why? For a given periodic time, there's a given radius, right? So we can definitely tell what should be the radius, okay? We can apply to this equation. We can use these equations. See, we can use these equations, okay? We can use these equations and put 24 hours here. Pay attention, put 24 hours here, put G here, put mass of Earth here, and find R, okay? So it is a definite radius, okay? It is a definite radius. So it's around 36,000 kilometers above Earth, okay? The geostationary orbit is around 36,000 kilometers above Earth. And the best scenario is, and the most complex and the problematic scenario is, since it is a stationary orbit, all the communication satellites must be on this on that orbit, okay? So there's a lot of traffic on that orbit, like high level, okay? So there's a lot of traffic in this geostationary orbit, okay? There's a lot of traffic. Why? Whoever involved in communication should be in that orbit. It's the same orbit everyone's using. You can't just change the orbit. See, everything that involves in communication have to be in this orbit. Now definitely technology have changed. Now we have small orbits, very small satellites going really fast around Earth, creating it's not a communication system, it's a communication grid, which ground antennas can shift between satellites really fast. It's a very different technology now. But in the conventional system, all the communication satellites, all the geostationary stuff should be in the same orbit. So it is an orbit with a lot of traffic, okay? It's an orbit with a lot of traffic, thousands of, and if some kind of a series of collisions happens in that orbit, then our communication system is in trouble, okay? If some kind of a set of collisions happen in that orbit, collisions would continue into other collisions, and there would be massive amount of collisions would destroy everything in that orbit, okay? It would destroy everything in that orbit, and then we are in trouble. That's why even now we are going to get rid of uh, space station, right? International Space Station. Now we are going to get rid of that. We don't like to keep it there. So there's a separate mission, I think, this year to push it away from that orbit and like just remove it to a different orbit and make sure that it would go in a different trajectory and go away from our gravitational system, okay? Because if a series of collisions start happening, then the whole communication network is in trouble, okay? Okay, so you can try, okay? You can try exercise 2 questions, but would find difficult because we didn't do much examples. But I think you would be able to do few questions, so try that. So finish exercise 1 and try few questions from exercise 2, okay? And I'll start around maybe 6:40. I'll start the heat discussion.